Hey everyone, in this lesson we're going to review the two main types of reactions in thermochemistry. Remember that thermochemistry is the study of heat absorbed or released during chemical and physical changes. So we're going to differentiate between the changes that absorb energy or absorb heat and the changes that release heat. So these two are called exothermic reactions and endothermic reactions. So let me move this over to the side. So I'm going to start with exothermic reactions. Exothermic reactions happen when heat is released in a chemical reaction. So heat is released, a chemical reaction. We're going to focus on chemical reactions because this is chemistry. Heat is produced as a product of the reaction, so it tends to feel hotter. So an example would be like if you light a torch, the energy that's released by light from the flame would be the heat that's released. So heat is released in a chemical reaction. So because heat is produced, reaction feels hot. Then on the other side, you have endothermic reactions, which occur when heat is absorbed. So in this case, heat is absorbed in a chemical reaction. Because heat is absorbed, it tends to feel colder. So think about like an ice pack that you snap, and if suddenly becomes a lot colder, that is a endothermic reaction. We can show the change in energy through energy diagrams, which I have like on the right over here. On the x-axis of the diagrams, the reaction pathway is shown. So basically it shows you the reactants, the stuff that reacts together on the left side, and shows you the products on the right side as you go down the x-axis. The y-axis shows the amount of chemical potential energy. So in this case, it is given in kilojoules. It can be given in joules, kilojoules, calories, but in this case, this is kilojoules. So in this example right here, we're going to examine the energy diagram, this energy diagram right here, for the combustion of butane. So for the combustion of butane, is just this equation. It's 2C4H10. It's a balanced equation. Plus, basically, butane plus oxygen becomes carbon dioxide and water. So if you look at it right here, you can see that you have the reactants, butane and oxygen right here on the left side, and then you have the products, carbon dioxide and water on the right side. So there's a couple things to note. You can see that the reactants start at 5,000 kilojoules, that's how much energy they have, and the end of the reaction they have 2,000 kilojoules. So we have a bit less. So let me actually make this a little bigger so you can see it a bit better. All right. So another thing to notice is before the reaction actually happens, some energy needs to be gained. Even though the products have lower energy than the reactants, some energy needs to be gained first for the whole reaction to happen. So this is called the activation energy. So if you want to find the activation energy, what you would do is you would subtract, or you would take the total energy when you have the activation energy minus the initial energy. So in this case, let me actually use my pen right here. We have this we have the 6,000 kilojoules, and remember we started 5,000 kilojoules. So our activation energy, our EA, is equal to, I'll just write it down here, 6,000 minus 5,000, which is equal to 1,000, and don't forget this is in kilojoules. So that's our activation energy right there is 1,000 kilojoules. And so once it gets enough energy inputted in, the whole reaction can proceed, and this butane can become carbon dioxide and water. Another thing that you should focus on right here is this delta H. It's the change in enthalpy, or total basic heat energy. This is simply the difference in the energy between the products and the reactants. In this example, the products have lower energy than the reactants, so the delta H right here is going to be negative. So the way you calculate that is you take your final energy, so that's 2,000, minus your initial energy, so that's 5,000. So you have to do, let's take it right here, so it's going to be delta H is equal to, it's going to be 2,000 minus 5,000, and you know that's going to be a negative number. That's going to be negative 3,000 kilojoules. So right there, since you know that the delta H is negative, we know that this is going to be an exothermic reaction. So if something's positive, it's going to be endothermic, but in this case, it's negative, which means energy is being released. So the change in the enthalpy is going to be negative 3,000. So if you had an equation, you'd actually write this on the product side, this 3,000 kilojoules, because it's being released. So let me, whoops. I'm going to move this over right here, and I'm going to write this, even though it's negative right here, it's not going to show up as negative energy. It's just going to show on the product side. So it's just going to come up as plus 3,000 kilojoules in this equation because those 3,000 kilojoules are released. So going from that, in an endothermic reaction, right here is an example of an endothermic reaction, we have the products have more energy. You see right here, the product C has more energy than the reactants. In the energy diagram, this means that the products are higher than the reactants, so the delta H, that change in enthalpy, is going to be positive. So if we wrote down the equation, it would end up looking something like this, where we have, in this equation, it's just going to be A plus B, and then you have to add energy right there. We'll put energy, actually let me make some more space right here, plus energy goes to C. So in this case, it would just be some energy amount right there, how many ever kilojoules of energy is required. And this shows that energy is absorbed. So now we're going to look at two different scenarios with just equation. So in this first one right here, you can see shows carbon and oxygen combining to form carbon dioxide. The delta H in this case is negative 393.5 kilojoules. So since you see it's negative, you know automatically that it's going to be a exothermic reaction. Exothermic. This means that energy is being released, and that's why it's negative. So the potential energy diagram would have the products that are lower than the reactants. So let's draw this little energy reaction diagram. So I'll put the reaction right here. And the potential energy right here. So you know that we're going to first start off with the reactants. And since energy is released, the reactants will have higher energy than the products. So let's say we'll put the reactants right there. And we just need to know that the products, it's going to be just a difference of negative 393 kilojoules, 0.5 kilojoules. So I'll just say that this is a pretty rough sketch. So I'll just say it's like this much down is minus 393.5. So remember, we start with our reactants. I'll put an R right there. And then we have the activation energy. And then we go down to the products, which are right there. And so that shows how you get the energy diagram of an exothermic reaction. So the next one is actually, this one's a little different since it shows the energy in the equation. So you can see right here, the energy is on the reactant side. So this means that energy is being put in to the reaction, which makes it an endothermic reaction. So right here we have carbon and hydrogen along with some energy come together to form ethylene, which once you get to organic chemistry is going to not be your best friend. But here, since the reactants, the energy is on the reactant side, it's showing that energy is being absorbed. And so because this is an endothermic reaction, the delta H is going to be positive. So let me write this as, say, endothermic reaction. And so your delta H is positive. So it's going to be positive. This means that the energy diagram would have the products higher than the reactants. So let me give myself some more space right here to draw this energy diagram. So same thing. Put a little. We have the potential energy on the y-axis and the reaction pathway on the x-axis. And so remember that your products will have higher energy than your reactants. Okay, so let's start off. Let's keep it low, right? We'll have your reactants start there. Remember, your products are going to have higher energy. So let's say we'll get the products around right here. Products. So what happens is, remember, you always need an activation energy in endothermic reactions. It just means this goes a little higher than the products, and then comes back, and then the energy stops right there. And so that's how you do these different, and yeah, if you draw the delta H is equal to, it's going to be positive 52.4 kilojoules. All right, just do a quick recap. We know that we have two different types of reactions for thermochemistry. There's endothermic reactions and exothermic reactions. Exothermic reactions are a reaction where heat is released, and so because heat is released, it's going to feel hot. So the energy diagrams are going to look just kind of like this one right here, where you start off with your reactants having higher energy than a little activation energy, and the products end up having a lower energy. Where activation energy is the energy just needed to just get that reaction going, and the delta H, or change in enthalpy, is the difference in energy between the products and the reactants. So in exothermic, it's going to be negative because the products have less, whereas in endothermic, like this one right here, the delta H is going to be positive, which let me actually write that in right here. So in this case, this is the delta H, and so you know that's going to be positive because whatever this number is, you know that's going to be higher than the reactants.